In the last video, you got the chance to play around with the universal collider simulation to hopefully see how limiting and excess reactants work. And so that sets up the groundwork that we need to talk about mole ratios, which we'll be talking this in this section 9.2. This is where we actually start to get into the heart of stoichiometry, which is really just a really fancy, glorified way of saying conversions. And you'll see what I'm talking about once we're done with this video. All right, so in this section 9.2, we're dealing with the mole-to-mole conversion. And so for this video, we'll be going through the terms of stoichiometry, dimensional analysis. This is setting up the tables to make conversions that we've used before. We're bringing it back for this section, and then we'll also be using mole-to-mole ratios. All right, so now stoichiometry, as I just said, is that it's just another way of saying conversions. A more technical way to look at it is that we're using a balanced chemical equation to connect and relate different amounts of substances in that chemical equation. Now, that's an important part, that we have a balanced chemical equation. We spent some time in Unit 7 balancing those chemical equations, right? That follows the law of conservation of mass, saying that we cannot create or destroy mass, which means that what you put into one side of a chemical reaction, you get it out in the product side of it. It might have a different form, but it's still the same elements and it's still the same number of atoms. Again, the reason that this is important for stoichiometry is that we use the balanced chemical equation for our mole ratio. This is where our conversions start to take shape. All right, so now if we're given a chemical equation like this, the synthesis of water, where we're taking 2 moles of hydrogen gas and 1 mole of oxygen gas, and they combine to make liquid water. If we go through and we count the number of atoms that we have for each of these on both left and right sides of this reaction area, you'll see that for hydrogen, you will take 2 coefficient multiplied by the 2 subscript, and this gives you a total of 4 hydrogen atoms. If you do the same to the right side on the water molecule, we'll have a coefficient of 2 multiplied by a subscript of 2 to give us 4 hydrogen atoms as well. And next we'll do the same to the oxygen, where we take a coefficient of 1 and multiplied by 2 for the result of 2 oxygen atoms. And on the right side, if we do take this coefficient of 2 multiplied by 1 oxygen, we get the result of 2 oxygen. So this is working out well as a balanced chemical equation. So now we can grab some information from here and make a mole ratio. So what this would look like if we focused on hydrogen and set up a ratio to the oxygen, according to this chemical equation, you'll see that we have 2 moles of hydrogen gas, and that corresponds to 1 mole of oxygen gas. And we set it up in this way as a proportion, with 2 moles of H2 on top and 1 mole of O2 on the bottom. So now, a good question to ask is, why is the hydrogen on top and not on the bottom? And the reason for that is that, well, there's not a good reason for it. We can totally do it the other way, and it's still the same information. It's just a different way of writing it. So now these 2 ratios represent the same information, just set up in opposite ways. And the reason that we need this is that sometimes we'll be using the ratio on the left, sometimes we'll be using the ratio on the right, and it just depends on the problem that we're working. Whatever information they give us to start with, we need to set up our problem in a way that will cancel out the moles unit. All right, so this is relating my 2 reactants, hydrogen and oxygen, and setting up a mole ratio from that. But you can also compare products and products, or you can compare reactants and products across the chemical reaction area. All right, so in this case, we're still sticking with 2 moles of hydrogen gas, and we compare it to the 2 moles of water that we're making as a product. Again, you just set it up in the same way as a proportion. 2 moles of H2 set over 2 moles of H2O, or you could have the opposite of this with 2 moles of H2O on top set over 2 moles of H2. And so again, these are the mole ratios that we're setting up to use in our stoichiometric calculations. And one thing that I should point out on this one is that even though we're setting up these proportions, we're setting fractions in a way, but we're not cross multiplying in these. It's very important. It's a very common mistake, so look out for that. Is that even though we're setting up the ratios in this way, we're not cross multiplying to get a result out of it. We're doing something a little bit different, which we'll be seeing in this next slide where we get into an example of the stoichiometric calculation. So let's get started on some of these stoichiometric calculations that we can see. And the first type we'll see is the mole-to-mole conversion. So now I want to give you this graphic here and tell you what this means, because this will essentially be a map that we can use for any type of problem. And I've said this before on the dimension analysis and mole conversions that we've done before, is that these problems are all basically the same. Once you know how to set it up and you know where the pieces go, the numbers and the names can change, but the process is still all the same. All right, so basically in this graphic, I have every problem that you might see, just as long as you know where to place the numbers. So what I have here is that I'm starting with some amount of moles of a substance. In this case, I'm just calling it compound A. This is the first thing that we look at. And notice that this arrow follows to the moles of compound B. So notice that my units are staying with moles and moles, but I'm just changing if I'm talking about compound A to compound B. And what's connecting them is this conversion arrow. What I'm using for that conversion is the mole ratio that I have set up here. So taking it back to the dimension analysis, the table that we set up, we just have moles starting in the top left. That bottom section, you leave it blank. And in the next section, we set up the mole ratio with the unit that we started with on top moves to the bottom. So in this case, I'm taking moles of A, set it on the top. This comes from the problem. And then according to my mole ratio, I'll set moles of A at the bottom. And then the moles of my second substance will go on the top. All right, so make sure that you save this. Again, if you know how to read this, you know how to do every problem. All right, but let's actually get into a problem that you'll be seeing, a problem that you should be familiar with to actually make sense of this graphic and use it as an aid. So let's say that we have this problem. How many moles of oxygen will react with 6.0 moles of hydrogen? Now remember that for these, what we need is a balanced chemical equation. And a lot of times you'll be given the equation. Sometimes you'll have to figure out yourself. Those are really more of the challenge problems. But in this example, we'll just start with our chemical reaction. This is already balanced. You can tell because, let's see, on here I have 2 times 2 hydrogens. That gives me 4. And on the right side, I will have 2 times 2 hydrogen, again, 4. And for my oxygen, 1 times 2 oxygen gives me 2. And then 2 times 1 oxygen will give me 2 as well. So it's a balanced chemical reaction. We're good on that front. All right, so the first thing we need to look into is take this balanced chemical equation and set up a mole ratio. Here we're just going to set up our options that we can look at to relate hydrogen to oxygen. So in this one, I'll start with the hydrogen. So I'll take 2 moles of hydrogen, H2, and set that over 1 mole of O2. The other way to look at this that is still technically correct, and it's still just another way of looking at it, it is to flip that. So we have 1 mole of O2 set over 2 moles of H2. And that takes care of our whole first step. Second step is to set up the dimension analysis table again. This table that we've had so much practice with. So let me go ahead and pull that in. So we'll be pulling information from the problem in this one. So look for the number that's given to you. So in this case, we have 6 moles of hydrogen. That's your starting quantity. So go ahead and write down 6 moles of H2, and then you'll set up your table around it. Remember that in this next step, this is where we set up the mole ratio. So I need one of these mole ratios that I just set up to put it on there. Now, which one do you use? Well, make sure that you use the one that has the unit you started with move to the bottom. So in this case, I have O2 in the bottom. That's not what I want. I need H2 to go on the bottom. So I'll be using this mole ratio on the right that I have. So I'll just copy that over with 1 mole of O2 set over 2 moles of H2. And that takes care of step number 2. Step number 3 will be to cancel the matching units. This is just to make sure that you did set it up right and that you're not doing anything wrong. So in this case, I have mole of H2 on my top left and mole of H2 to the bottom right, and this is matching my unit. So we'll cancel these out. Notice that if you had put O2 in the bottom, you couldn't cancel it with the H2 on the top. So that's why this other conversion factor, the mole ratio, wouldn't have worked. So it's a really good safety check to know that if you're going through the problem the right way. And then finally, my last step is to calculate. Remember that this table has a mathematical meaning where I'm multiplying the numbers that are across from each other and then divide by what's on the bottom. So again, if I take that expression and I simplify it, I get 6.0. Got rid of the unit on this once again. That's 6.0 times 1 mole of O2, and that is all divided by 2. There's no unit on the bottom because I canceled that one with my top unit. All right, so now carry that through. Sometimes you might need a calculator. Sometimes they'll be very straightforward, but the answer for this one will be 3.0 moles of O2. And just like that, this is the pretty much the strategy for all the problems you'll see. It's just a matter of being able to read your problem and finding information from there. You're just looking for well, in this section we're only looking for one. Excuse me. We're only looking for one piece of information. We're looking for the mole ratio and that you're able to pick the right one. So make sure that you save these notes. Definitely save this graphic because this will save you on every problem that you have to do. And so let's just get some practice on this one before we take it to the next step. It'll still be the same skill. We're still doing the same process. It's only going to get a lot bigger. So it's important that you're confident with this small stuff we're doing for now. All right, so in the next section, we'll be adding grams to the mix. But again, still same process. So make sure that you get a lot of practice on this one and that you feel confident on how to work these problems.